In the previous video, we saw photoelectric effect and how the observations of photoelectric effect and the properties of photoelectrons uh, pointed to light or electromagnetic radiation as behaving as particles rather than waves. And these particles were given the name of photon. Now we know that particles that have a mass or objects that have a mass have a momentum associated with them given by mass times velocity, at least in classical physics. So photons are expected to have momentum as well, since they are particles. However, something unique about photons is that they do not have a mass. So this is a case where you have a massless particle having a momentum, which could not have existed in classical physics. In classical physics, in order for something to have momentum, it would have to have mass. So photons have properties similar to particles. They interact as a unit rather than as waves in collisions or when absorbed by matter. So photons, like particles, carry momentum despite being massless. And one illustration of the particle nature of light comes from observations involving comets. Now, comets are objects that appear every once in a while, and they have a long tail, which is very remarkable. So this is a picture of a comet. Now, it's seen that so what's shown in this diagram here is you have the sun here, and then this is the path of a comet. Now, as the comet moves on its path, at any instance, the tail of the comet is always pointing away from the sun. So as the comet moves, the direction in which the tail is pointed is changing in such a way that at all times it's pointed away from the sun. And the reason for that has to do with light coming from sun, consisting of particles and behaving like particles rather than waves. So tails of comets, which are made up of gases and dust, emanated from the comets. These tails always point away from the sun, which is evidence of photon momentum. When photons coming from sun collide with particles in the tail, some of their momentum is transferred to these particles. And then these, in response to that, move away from the sun. So that's the explanation of why the tail always pointing in a direction away from the sun. Now we have seen that momentum is conserved in classical physics and then also in special relativity. And it turns out that momentum is also conserved in quantum mechanics. Conservation of momentum was used to describe scattering of X-rays when they interact with matter. So if you have X-rays interacting with matter, they scatter in different directions, and the properties associated with the scattering were first observed by an American physicist by the name of Compton. And he described mathematically how that scattering of X-rays from matter is consistent with conservation of momentum. This scattering in his honor is known as Compton scattering. The basic setup for Compton scattering is shown here. So you have This here is an electron in the matter in some substance. And then what you see here is an incoming X-ray radiation, X-ray photon, which has an energy of h times f, where f is the frequency of this photon and h is the Planck's constant. So it hits the electron, and after the collision, the photon is deflected in this direction. And the energy of that photon has changed to E prime, which is equal to h times f prime. So the frequency has changed from f to f prime. If the frequency has changed, then wavelength has also changed from lambda to lambda prime. And then after the collision, the electron itself, so after the collision, the photon moves in this direction, the electron, which was initially at rest, is now moving in this direction. So it's kinetic energy of that electron changes by an amount E minus E prime, because that's the difference in the energy of the photon, which is imparted to the electron. So it turns out that both energy and momentum are conserved. In order for energy to be conserved and momentum to be conserved, the momentum of photon has to be taken to be P, or the momentum, equals Planck's constant divided by its wavelength. So it's not mass times velocity. Of course, it doesn't have a mass. Photons don't have mass, so that definition is inadequate. In order for energy and momentum to be conserved, the momentum of the photon has to be defined as h over lambda. Compton effect is noticeable for X-rays because their wavelength is so small. There are very high energy photons, which means their wavelength is very small, and therefore the momentum is large. For visible light, which have long wavelengths, momentum is extremely small. That's why you don't see, when photons of visible light strike a mirror, for example, when light hits the mirror, you don't see the mirror recoil by the impact. So in the macroscopic world, in our day-to-day world, we don't notice, we don't experience the effect of Compton scattering, which is very, very much like most other quantum phenomena, which are not observable directly in the macroscopic world. Now, this definition of photon momentum, h over lambda, is consistent with relativistic momentum that we saw in the previous chapter. You will recall that the energy and momentum are related by this equation. Energy square equals momentum times speed of light square plus mass of the particles times c square squared. If you're talking about a photon, the mass is 0. So the second term drops out, and E squared is simply equal to the square of PC squared. So if you solve this for P is E over C, and for a photon, the energy is HF or HC over lambda. And when you divide that by C, P comes out to be H over lambda. So P equals H over lambda is the momentum of the photon that we get from special relativity, which is consistent with this. Let's look at problem number 45. So in problem 45, we have to find the momentum of 100 keV X-ray photon. And then in the second part, find the equivalent velocity of a neutron with the same momentum, and then neutron's kinetic energy. So we first gather all the information that's given to us. Energy is 100 keV, or 10 raised to 5 electron volts, which when converted to joules by multiplying with 1.6 times 10 to the negative 9 comes out to 1.6 times 10 to the negative 14 joules. So we'll be working in SI units here. Energy being hc over lambda, which is pc, or p is E over c. So you divide that number for energy by the speed of light, and that gives you a momentum of 5.33 times 10 to the negative 23 kilograms meters per second. So that's the momentum of this X-ray photon. Then in part B, we have to find the equivalent velocity of a neutron with this. So if you had a neutron with the same momentum, what would be its velocity? And we're going to assume a non-relativistic equation. So in classical physics, momentum is mass times velocity. So velocity is momentum divided by mass. So if you can look up the mass of a neutron, which is 1.67 times 10 to the negative 27 kilograms. And when you divide the two, you get a velocity of 3.19 times 10 raised to 4 meters per second. And as you'll notice, this is much smaller than speed of light, which is 3 times 10 raised to 8 meters per second. So our assumption of non-relativistic equation was justified in hindsight. And then in the third part, what is the neutron's kinetic energy in keVs? So now that we have established it is indeed a classical situation, a non-relativistic situation, we can use the classical equation for kinetic energy, 1/2 mv squared. So when you calculate that, it comes out to 8.51629 times 10 to the negative 19 joules. And then when you divide it by the charge of the electron, you get the energy in electron volts. The problem asks us to find the kinetic energy in keVs, so you divide that by 1,000. So 5.32 times 10 to the negative 3 keV. And look at how small this number is compared to the energy of the photon, which was 100 keVs. Now, we have seen how, when it comes to photoelectric effect, light behaves like a particle. So photon basically is the name that is given to that particle. Whereas there are other phenomenon in which light behaves like a wave, and there's no way to explain those phenomenon if you assume that light is a particle. So, and one property of waves that is interesting and applicable in this case is interference. So waves show interference effects, whereas particles do not. And to understand interference, let's go back to optics as a detour. So if you imagine, this is the famous double slit experiment. If you imagine a very narrow openings in an opaque plate, and then on the left, you have a source of light. So that light, when it hits the two openings, uh, they're coming from the same source here, so they will be in phase, meaning their peaks and valleys of these two will occur at the same time. Now, on the other side, you have a screen, and if you follow light coming from this slit as it hits that point on the screen, and then compare it to this light, which is coming from a little bit farther and hitting the same point. Now, at the opening, at the slit, the two lights were in phase, meaning their peaks and troughs were occurring at the same time. But in going from here to this point, this light had to travel a shorter distance, this light had to travel a longer distance, which means the the peaks and valleys are probably not going to occur at the same time anymore. If this is the wavelength of this light, then whether or not the peaks and valleys coincide here will depend on what the path difference is. If the difference in path between these two is equal to the wavelength or a multiple of the wavelength, then they would still be in phase. However, if it's half a wavelength, then they'll be out of phase. And if they're out of phase, if the peak of one coincides with the trough of the other, then the two will completely cancel out. So what you'll get here is darkness. On the other hand, if the path difference is a multiple of wavelength, then the two waves, when they meet here, will enhance each other. And that gives rise to a bright spot here. And that's called constructive interference. This is called destructive interference. But basically, the idea is this phenomenon of interference can only be described if you treat light as a wave. Because when you talk about peaks and valleys, you're basically talking about a wave. You can't talk about peaks and valleys for a particle. So the crux of the matter is the phenomenon of interference can only be described if you assume that light is a wave. On the other hand, the phenomenon of photoelectric effect can only be described if you assume that light is a particle. So this leads to the idea of particle-wave duality. So traditionally, we have seen waves and particles as being two distinct entities. If something is a wave, it cannot be a particle. If something is a particle, it's not a wave. But in electromagnetic radiation, we see both behaviors, both particle-like and wave-like. So double slit interference, for example, that I just showed, can only be explained if you assume that light is a wave. Photoelectric effect can only be explained if you assume light is a particle. So the conclusion that we draw is, depending on the setup used to observe electromagnetic radiation, it can behave as either a particle or a wave. So if you have an experimental setup to observe photoelectric effect, light will behave as a particle. But if you have an experimental setup to observe interference, light will behave as a wave. So we'll continue this discussion in the next video where we'll talk about the wave nature of matter.